Each tunnel segment weighed more than the equivalent of 24 space shuttles. Between them, they contained enough concrete to build a pavement around the Earth twice. No machine in the world could lift one into the air and put it into place. And these engineers had to get each 55 million kilogram piece off dry land and into the middle of the Oresund Strait. The answer was to turn them into rafts and sail them. First, any holes were plugged with giant steel plates, each weighing more than 3,000 kilograms. These enabled the gigantic concrete structures to float, but there was still no way to transport them to the water. So an ingenious lock system was built to bring the water to them. The end of the assembly line was surrounded on 3 sides by dikes. The fourth was closed by a huge movable wall, and the basin was flooded to more than 9 meters above sea level. It took 100 million liters of water. Even when afloat, 4 23,000 kilogram winches were required to move each segment, and 2 more winches to steer it to the deep end of the basin. When the water returned to sea level, the segment was ready to head out. Then, when it was over the trench, there was a new challenge: sinking it. Forcing a raft this big underwater was not an easy task. The trick they used was ballast. Water was pumped into special tanks very slowly and evenly to keep the segment horizontal. 4 massive cables helped guide its descent. Precision was paramount, so it could be accurately connected to the rest of the tunnel. Winch operators used GPS and depth gauges to make sure they kept on target. The margin of error was less than 1¼ centimeters in any direction. Divers installed a temporary frame to help guide it. Then, when it reached the seabed, winch operators pulled it tight against the previous segment. Any seawater trapped between the segments was pumped out. The steel panels were removed, and to keep the tunnel from ever floating again, concrete, almost a meter thick, was poured the entire length of the roadway, then boulders piled on top. The system worked flawlessly for the first 12 tunnel segments, but the 13th still got special handling. It was officially numbered 12A for superstitious reasons, but unfortunately renaming it wasn't enough. On Tuesday, the 4th of August 1998, wind and current conditions in the channel were perfect. The tow-out of the new tunnel element started uneventfully. By midday, element 12A had been guided into position. At 3:30, pumps added ballast, slowly sinking the unit beneath the waves. Then, suddenly, something went very wrong. The segment started to tilt, and then collapsed. A huge explosion of water blasted 30 meters into the air. The segment plunged to the bottom. Crews on the pontoons shut down all power, fearing they'd be electrocuted. It was hours before they figured out what had gone wrong. The verdict was human error. A steel plate hadn't been sealed correctly. Water pressure had forced it open and flooded the segment. The winches weren't able to hold the added weight. Luckily, no one was injured. But what about tunnel segment 12A? Extensive testing confirmed it was still usable, but valuable time had been lost. Oresund's builders could have chosen a different method to build their tunnel. They could have bored a tube under the seabed. This is what Denmark did 2 hours away from Copenhagen, where rail and road needed to cross a channel called the Great Belt. This was the site of a disaster far worse than the Oresund's. To dig the 2 train tunnels, they brought in 4 enormous boring machines, each 90 meters long. The front end is a drilling head weighing over 100 million kilograms and measuring 7 meters across. The cutting head chews up soil and boulders. An auger shuttles the ground bits to a conveyor belt, and they're eventually dumped on a small train. As each tunnel boring machine worked its way underground, it also installed pre-made wall segments, 62,000 of them. The problem with boring was that the ground could be unpredictable, and this was how disaster struck the Great Belt. A boring machine hit a water pocket. At first, water began to drip in. Then it started to pour. A special safety hatch should have contained the flood, but it had been left open. Water flooded one tunnel, crossed through the emergency tunnels, and flooded the second. It took a year to get the project back on track. The tunnel here differed from the Oresunds in another way. It went right across the channel, so heavy trains wouldn't have to use a bridge at all. This gave engineers more design options than they had at the Oresund. They were able to build a suspension bridge, and they did so in a big way. The second largest in the world, spanning nearly 2,700 meters. The towers reach up 250 meters, almost 30 meters taller than the towers on the Golden Gate Bridge in San Francisco. Unlike the Oresund, this bridge's structure depends on two main cables draped over the towers. These monster cables are almost a meter thick and around 3 kilometers long. The main cables are actually made up of over 18,000 wires, each thinner than a pencil. They're not twisted together, instead they're stretched next to each other and bundled. The finished cables weigh over 9.5 million kilograms each. The trick to making a suspension bridge is anchoring each end of the cable. For the Great Belt Bridge, the anchor blocks were enormous, little islands unto themselves. Each weighed more than 300 million kilograms. Cable-stayed bridges like the Oresund don't have anything like this. Anchor blocks are just used for suspension bridges. But the cable can't just be buried in the concrete. It would pull right out. The load has to be spread over a large area. So as the cable enters the anchor block, the wires branch out into smaller and smaller clusters. By the time the Great Belt cables reach concrete, their load is spread over 64 square meters. It's easy to see the cable's flexibility in the anchor block.
It would take a little time but it will actually start to move. Now it's moving a little, 3 or 4 millimeters, but it's moving all the way from the top and down to the anchor plate.
This was exactly the kind of flexibility that the Oresund Bridge needed to avoid. It had to be rigid in order to carry the tremendous weight of car and rail traffic. And it needed awesome engineering if it was going to break world records. Having to build the bridge section this high and this huge created the biggest challenge of the entire Oresund project. Engineers were hurtling full speed towards the July 2000 deadline. The last stones had been placed on the artificial island. The tunnel elements had been sunk. Now it was time to build the world's longest cable-stayed bridge for car and rail. Construction began with the towers. At 60 stories, they would be by far the highest freestanding double-legged bridge towers in the world. 2 giant legs would be connected by a massive crossbeam just below the roadway. Above the deck would be open space. There were 2 reasons for this lack of crossbeam above the road. It kept the bridge design looking clean, but it was also in case of a plane crash. If this computer-animated disaster were ever to become reality, freestanding towers would help the bridge survive. Without a crossbeam above the road, the towers would be more flexible. In In the event of a crash, less of the impact would be transmitted to the rest of the bridge, and it would stand a better chance of survival. The building of the towers started on land. Like the tunnel segments, the foundations were made in a dry dock. They were enormous, the base of each covering 1,500 square meters, enough land for a house, garage, and garden. Their dead weight was over 18 million kilograms. This was a lot lighter than the tunnel segments, but moving them was much trickier. They were 22 meters high. The Oresund Strait was only 7.5 meters deep, so they couldn't be floated like a raft. They had to be carried. No vessel existed that could do this, so the Oresund engineers built one. They started with two immense barges, then connected them at both ends to create a kind of catamaran. Then the dry dock was flooded, so the catamaran could sail over the foundation. It took 5 enormous tugs to tow this contraption into the channel. At the bridge line, the foundation was lowered into a pit that had already been dredged into the seabed. GPS helped guide it to within 8 centimeters of its target. At this stage, the foundation stuck out of the water by just 3 meters. Soon each stump would grow another 180. Each embryonic tower became its own self-contained construction site, outfitted with enough equipment for a small factory. The 2 legs for one tower climbed into the sky in 4-meter sections. One always stayed 12 meters ahead of the other, so the massive cranes didn't get tangled. When the towers reached 44 meters, it was time to add the crossbeam. Then, at about 80 meters up, a steel box to hold the stay cables was integrated into the leg. Another box was added every 12 meters. From the outside, the towers look solid. But in fact, they're packed with equipment, including a lift. A hatch in the top of the tower reveals the penthouse view. At the same time as the towers were being built in the middle of the Oresund Strait, the double-decked spans were being assembled at shore. They were immense steel and concrete boxes, about 140 meters long and 23 meters wide. The top would be a 4-lane highway, while the trains would go inside. The designers decided to put the train tracks in a special cement trough. If a train was to derail, they hoped this liner would keep the train on the bridge. The bottom of the spans may look solid, but like the towers, they're hollow. And they too housed equipment critical to the bridge. The bridge contained a total of 18 million kilograms of steel, and steel has a mortal enemy: rust. Rust could potentially destroy the bridge from the inside out. Paint can add protection, but it was not economical to paint so much surface area. So instead, the Oresund Bridge was constructed to contain a vast system of dehumidifiers. These keep the air inside below 60% relative humidity, and no moisture means no rust. Regulations required crews to inspect every part of the bridge. This was obviously a prudent measure, but a big challenge, because the underbelly of the bridge was 60 meters above water. Even on the road, workers had to be protected without interrupting car and train traffic. Luckily, the Oresund engineers had planned ahead. Hanging under the bridge is a spectacular motorized gantry. The Oresund link has one of the few gantries in the world that can run the entire length of the bridge. Most gantries would be stopped at the bridge towers. But this gantry pivots to squeeze between the supports. On the other side of the tower, it spins again and continues on its way. Once the crew is in the right place, the Oresund's gantry works like a gigantic Swiss Army knife, packed with exotic contraptions. A hydraulic arm can carry a worker outside the trusses, up and over the roadway. The access is phenomenal and, most importantly, doesn't interrupt the flow of train and car traffic. Hanging so far above the water, the arm gives access to equipment like this device, created especially for the Oresund bridge. It's a damper to reduce cable vibrations that could potentially shorten the life of a bridge by decades. The gantry has another gadget used to inspect the towers. This hanging bucket can lower workers 60 meters, right down to the waterline, where they can check the concrete for cracks and even change the light bulbs that guide ships through the navigation channels. From the gantry, it's easy to see that the deck was assembled from pieces. It's less obvious how the pieces got here. The enormous segments were pre-assembled several kilometers away on shore. The good news was that they only weighed 5.5 million kilograms, not 18 million like the foundations, or 55 million like the tunnel elements. The bad news was that the tunnel and foundations were lowered into place. The bridge spans needed to be lifted, 60 meters up, and then held dangling in the air. By any measure, the Oresund link was one of the most ambitious engineering projects of the 20th century. The contractors built from scratch an artificial island 9 kilometers around. They ground through 4 kilometers of ultra-hard Copenhagen limestone. And they pieced together the world's largest submerged tunnel. Now, with just 1 year left, it was time to begin the last and most spectacular stage of construction. Finally, the bridge would start looking like a bridge. All the planning and all the calculations would be put to the test as the main span was put into place. It had to be high enough for ships to pass under and strong enough to carry speeding trains and cars. No one had ever built a bridge like it. What was required was the largest floating crane on Earth, capable of lifting more than 7 million kilograms, the equivalent of 30 Boeing 737s. It was called the Swan, and this was her moment of glory. The Swan had to use 75% of her total strength to lift each span. The highest span went right next to the tower. Then crews attached cables. The first cable was 50 meters long, and each new cable would be longer than the one before it. The longest would be over 260 meters. The Swan brought in another span. The roadway cantilevered further from the tower and closer to a world-size record. This was the most vulnerable time for the bridge. Temporary scaffolding helped, but the bridge wouldn't be up to full strength until all the pieces were in place. Wind and storms could be disastrous. On the 14th of August 1999, the Swan installed the final roadway span on the bridge. Denmark and Sweden were connected for the first time. Denmark's Prince Frederik and Sweden's Crown Princess Victoria met at their first ever border crossing. For 9 years, the construction deadline had loomed over everything and everyone involved in creating the Oresund link. Finally, on the 1st of July 2000 at 11 p.m, the Oresund link officially opened for business, on time and on budget. The bridge may have been open, but the challenges didn't stop there. Now it had to pay back every penny spent on it, one toll at a time. The official budget for the bridge, tunnel and island was close to $3 billion, and the expenses would never stop. There will always be maintenance. Not long after the link opened, engineers discovered a problem with the guardrails. The bolts were corroding. One bolt was not much of a problem, but there were 16,000 of them, and if they failed, a minor fender bender could turn into a death plunge. Crews had to act quickly to prevent the bolts from rusting through. It was a big job, but it was better than waiting now and having to replace the bolts later. That would have required tearing up the concrete. Stopping the corrosion started with removing the nuts and blasting the bolts clean. To keep out moisture, crews coated the bolts with gel and used better fitting washers. Maintenance and everything else that happens on the bridge is monitored in Sweden from a building near the toll plaza. Hidden inside is a high-tech command center.
Traffic center, Arne. Okay, he's coming to work with
30,000 points of information from the bridge feed into the control room computers. Operators constantly monitor safety. There are 256 cameras on the link, too many for operators to monitor, so a computer helps. It's able to recognize stopped cars and cars going the wrong way. When it spots trouble, it alerts the operators and shows them the appropriate camera. Operators can also manually control the cameras, which have incredible zooms. One of the Oresund link's pleasant surprises can't be seen from the control room. It's underwater. The 51 bridge piers have had an unexpected environmental impact. They've become artificial reefs, covered in mussels and plants, providing food and shelter for sea creatures. Environmentalists who were originally against the Oresund project now document an explosion of life here. Creating a fixed link across 16 kilometers of the Oresund Strait had been a dream for generations. It was a monumental engineering effort, pushing technology to the absolute limit and establishing new world records, from the coast of Denmark to the coast of Sweden. The largest submerged concrete tunnel in the world. The world's longest double-decked bridge for car and rail traffic. And the tallest freestanding double-legged pylons on any bridge anywhere in the world. In its first 5 years of operation, more than 44 million people crossed the Oresund link, going to new jobs, to new homes, or just exploring. The Oresund link changed the map of Europe, successfully bringing 2 cities, 2 countries, and an entire continent closer together. It stands as one of the world's mega bridges.